I gotta say, that is a few tough acts to follow. Everyone has had such amazing presentations and such cool stuff. I'm hoping I can continue the trend, we'll see. So, I will go ahead and put this up behind me as I talk, because also, who says no to the opportunity to show themselves with fire? Exactly. So, hello everyone. As was said, my name is Nicole North. I'm currently a 5th-year graduate student at Ohio State University, and I'm hoping to complete my PhD in analytical chemistry by the spring of 2024. It feels ironic to be standing here sharing my academic journey while preparing for another graduation. But I also think it gives me a really unique perspective and an opportunity to address you not only as an alumnus, but also a fellow student simultaneously. So my current research focuses on combining machine learning and its applications in deciphering complex chemical environments, both on our home planet and in the outer reaches of the solar system. Specifically, I've dedicated my studies to ocean worlds, which are basically bodies throughout our solar system that are theorized to contain liquid water beneath either a rocky or icy surface. My research has taken me some really fascinating destinations, theoretically, focusing primarily on the moons of Saturn. I look at Titan and Enceladus, basically nailed it.
Very fun.
So the roots of my graduate work and my fascination with planetary science really trace back to what I worked on in my undergraduate years. When I first came to UNI, I was actually undecided, and I decided to attend a presentation in the biology department on black bear migration. I remember watching the seminar, and the speaker was really passionate about black bears, and I remember not knowing what I wanted to do, but I knew I wanted that. Whatever I got to do to get that. And so that next week, I actually changed my major to biology and began focusing on science. So my journey toward a career in research really commenced with an exciting opportunity to begin to do undergraduate research. I was under the guidance of Dr. Kenneth Eldersma in the biology department. This invaluable experience not only introduced to me the intricacies of research and what that looks like, but it also gave me an opportunity to refine what I was interested in when it came to the science. This became incredibly clear for me when I became so interested in how the instrument worked that we were doing our analyses on. And it was from that I realized I wanted to switch into chemistry. So after switching into chemistry, I actually worked for 2 different summers under Dr. Joshua Seabury from the chemistry department. His research had primarily at the time focused on the atmospheric chemistry of Titan, which is a really cool moon if you ever get a chance to do some reading about it. But I also was able to further solidify that passion basically by going on the first Wind Cave National Park trip with the Astrochemistry class. It was a great new experience, something that the department had never done before, and it was an opportunity for me to actually meet my new co-advisor, Morgan Cable from NASA JPL. That is a whole other story. I actually followed her around for a long time until I could get the guts to ask for a letter of recommendation, and she ultimately told me, she's like, do you just want to work together instead? And I was like, that's more than I could have asked for, sure, absolutely. So after my time on the Wind Cave trip and meeting my co-advisor, I was able to really hone in what I wanted to do for my graduate work. So as I was applying to OSU and as I was meeting with potential advisors, I was talking about this wanting to continue some planetary science, continue some atmospheric work. And that is where I met my current research advisor, Dr. Heather Allen at Ohio State. So she really encouraged me. She said, this is not typical for our regular lab research dynamic and what we typically do, but you should go try to get funding for this idea, because she thought it was a good one. And that's actually when we wound up applying for the FINESST, the Future Investigators in NASA Earth and Space Science and Technology, that mouthful. And so that actually was an incredible opportunity, because out of approximately 800 that were submitted, only 30 were funded. And it's pretty atypical to actually get funded on the first try when it comes to that program. And so that was kind of a confirmation that we were doing the right thing. And with that, I managed to basically buy out my time in graduate school. It really opened up a lot of opportunities that I may not have otherwise been able to work with. One of them is actually, like we were saying, attending the Planetary Science Summer School at NASA. So unfortunately, the year that I did it, it was still virtual due to COVID, but it was a great opportunity to meet with other scientists in different areas and really get to understand the amount of effort that it goes into planning a deep space mission. Obviously, when there's a bunch of money on the line, it becomes really, really important to understand both the risks and all the technological advances that need to be made. And so that was something that we were able to really dive into, and actually we were able to meet with engineers from NASA JPL's Team X, and their job is to actually take mission concepts from their science all the way into how it would actually be implemented in the real world, which was an amazing opportunity. I also had the opportunity this year to attend the inaugural Networking for Ocean Worlds retreat that was on Catalina Island, California. That was also an amazing opportunity. It was a great time to bring together scientists from all different areas. There were chemists and geologists and biologists and planetary science experts, people who were engineers from different actual startups actually making instruments for space. And it was just a really great opportunity to really kind of dive into what it takes to do these kind of planetary science missions, while also allowing me to share what I had been working on for the past few years and really feeling like I was able to contribute to that community as well, which was just a fantastic opportunity. I would say the most important thing that I have received from my time at UNI is a really strong foundation in scientific communication. I've been able to attend over 10 different conferences just during my undergraduate time, and that really gave me the skills necessary to be able to really translate my research to a variety of audiences, whether that is a general audience or general university audience like we have tonight, whether that is a general scientific audience where it's not just chemists, it's biologists and astrophysicists and all those different diverse areas. The suggestions that work for one group may not work with another, all the way down into really specific chemistry groups, which is really giving me the opportunity to dig deep into the theory and dig deep into the techniques, because each one of those audiences requires a completely different explanation, and that's a good thing. That's one of the most important pieces that I think in order to do impactful science, it's only as impactful as we're able to explain it. And so, with that, I would actually love to take the last few minutes of my talk to give you an overview of what we're looking at. So this is Enceladus. It's a beautiful moon just outside of Saturn. It's actually really interesting. Its name comes from Greek mythology and is named for a giant. But it's actually really interesting. This moon is actually fairly small. It is actually smaller than our moon, and the diameter is approximately the same size as that of Arizona, which is my favorite new form of measurement. And so what's really cool here is the reason that Enceladus became a topic of interest in the solar system is because it is the most reflective surface in the galaxy. So what happens is this entire surface of the moon is water ice, meaning that it reflects light really, really easily and really, really well. So during the Cassini mission, it became a target while they were also looking into the rings of Saturn and how they're made, what they're made of, where do they come from. They also wanted to go past all these moons because of all their kind of chemical intricacies that they were able to kind of detect from Earth. And so what happened was when they flew past this moon, they made some really, really interesting discoveries. The first is that this moon is erupting ice springs from the surface, almost like a geyser, but frozen solid pieces. And so that is interesting in and of itself. They were able to determine that it's actually feeding into one of the rings of Saturn and is leading to a good portion of its mass and why it partially has rings. But even better, it was also erupting ice rings that contain organic compounds. Organic compounds in this context are things that are primarily made with carbon and hydrogen, and therefore are really the basis of life as we know it. Like, we are made out of organic compounds, and so that is obviously a super exciting takeaway. What became really, really challenging, and they quickly found out, is identifying these compounds. If you don't know what could be there, and you're kind of trying to estimate what could be there, you don't want to eliminate something just because another study suggests that maybe that's not possible. The best way to think about it is actually if we think about a puzzle. So what they were doing is a method called mass spectrometry. In other words, they had a molecule, which exists here, but the problem is, unless we actually send physical samples back, it's impossible to see this. What we need to do is we need to be able to basically read pieces of it. We can only get it back through actual data. So what happens is this spacecraft moving at tens of kilometers per second collides with our molecule and turns it into a bunch of little pieces. But as anybody who's ever done a puzzle, if you try to evaluate the picture using only one or two or a small handful of pieces, it becomes almost impossible. And so what we have to do is we need to find the kind of higher level techniques in order to be able to do this. And there are a ton of groups working on this over the past few years. A good handful of molecules have been suggested as being present on Enceladus. But what we wanted to do is we wanted to know, can we advance this area through machine learning? Obviously, machine learning has kind of a buzzword. It has a lot of kind of intricacies behind it that I feel like are not well understood. Is it going to take over the world? I can't tell you that. What I can tell you is that basically when we're looking at it, the computers are trying to find patterns within the data. So the computer's job would be to look at this giant pile of puzzle pieces and actually try to find common puzzle pieces within that set to begin to match into other data sets. Our job, what we really wanted to look at was something called functional groups. These are parts of an organic molecule that tell us how it would potentially react either with other molecules or like what things is that molecule possibly capable of doing. And so we developed a machine learning algorithm using some other methodologies that were well established to basically look at the puzzle pieces and give us information about what the picture was. And we were fairly successful with this. We were actually able to identify a good number of functional groups on a test data set. It takes a lot of effort to really begin to apply these to other systems, and therefore it's so important to know how these assignments are being made. If I sit there and I look at these puzzle pieces and I say, I think it's a tree, you guys know, you know what this is. But if we're looking at a bunch of brown pieces, we're like, it could be a tree. I mean, that seems reasonable enough. But what we want to do is we needed to find methodologies to actually begin to understand why does it think it's a tree? Why do we think that these functional groups exist? And that actually led us down a really interesting path that really allowed us to start to tease out how these computers learn and how do you teach something chemistry when you can't explain it. And so with all of that, I would love to take one more opportunity to thank all the people that I've had in my life at UNI and all the support that I've gotten both from my faculty, staff, other students. My family's come out to see me today, my husband who's heard me give this speech probably 15 times by now. But I mean, the biggest thing is there's so many opportunities here at UNI to take advantage of and to learn from. And it really is about, yeah, as we were saying earlier, taking those opportunities, making them your own, betting on yourself, and really just seeing what you can do with it. Because as we've seen from our other amazing awardees tonight, that there's a whole vast, wide variety of really impactful things that can be done with your background at UNI. And I have been so blessed to be able to take this journey with all of you. But thank you very much.